The quantum observer effect. Does reality exist when no one is looking? You're standing in a dimly lit room staring at a closed door. You know what's behind it, a familiar space, a chair, maybe a lamp. But here's the question. Does that room still exist exactly as you remember it when you're not looking? Or does reality itself flicker into uncertainty the moment you turn away? It sounds absurd, even unsettling. But this is the heart of the quantum observer effect, a paradox that has baffled physicists, philosophers, and thinkers for over a century. It suggests that at the most fundamental level of existence, reality may not be something solid and objective. Instead, it may be fluid, shaped by the simple act of observation. To understand the paradox, you need to go down the quantum rabbit hole in the microscopic world of particles, electrons, photons, the very building blocks of everything you see. Things don't behave the way you expect. You would think that an electron is like a tiny marble moving through space in a definite way. But when physicists conducted the famous double-slit experiment, they discovered something shocking. When an electron is fired at a barrier with two slits, it behaves not like a solid particle, but like a wave. It doesn't go through just one slit or the other. It seems to pass through both at the same time, creating an interference pattern, as if it were a spread-out wave. That alone is weird enough. But then comes the truly mind-bending part. When scientists placed a measuring device at the slits to see which path the electron took, everything changed. The moment they tried to observe it, the electron chose one slit to go through, behaving like a solid particle again. No interference, no strange wave-like behavior. It was as if the electron only decided how to behave after it realized it was being watched. This is the observer effect. The mere act of measuring or observing something at a quantum level seems to force it into a definite state. But what does that mean for reality itself? If particles don't decide their state until they are observed, then before anyone looks, do they even exist in a definite form? Or is reality, at its core, just a blurry cloud of infinite possibilities waiting for consciousness to bring it into focus? The implications are staggering. It means that at the smallest scale, the universe does not operate on rigid, predictable laws. Instead, it dances between probability and existence, forming something real only when something or someone is there to witness it. It challenges everything you take for granted about the physical world. The chair, the lamp, the closed-door room, are they truly there when you are not? Or are they mere probabilities, waiting to be crystallized by an observer? Some physicists argue that this paradox doesn't mean reality depends on human consciousness, that observation in this case simply means interaction with another particle, like light bouncing off an object. But even this doesn't fully escape the paradox. Why does measurement change the state of reality? Why does the universe seem to respond to being watched? And this paradox stretches even further. If observation shapes reality, what happens to the universe beyond human perception? Before life existed, did the cosmos exist in some undefined, probabilistic haze? And if no one were left to observe it, would the universe simply dissolve into nothingness, waiting for something conscious to make it real again? The quantum observer effect has forced scientists and philosophers to confront an uncomfortable possibility, that the boundary between reality and perception is not as clear as we once believed. It suggests that the act of looking, of knowing, of being aware is somehow entangled with the very existence of the physical world. Einstein himself was deeply disturbed by this, famously asking, "Does the moon exist only when I look at it?" He believed reality must be independent of observation, that something must be objectively true whether or not we perceive it. But quantum mechanics continues to defy that expectation, leaving us with a world that seems stranger the deeper we try to understand it. So, does reality exist when no one is looking? The quantum observer effect offers no easy answer. Perhaps reality is more like a script, unfolding only when the spotlight of observation shines upon it. Perhaps everything you see, touch, and experience is only one version of what could have been, selected the moment you became aware of it. And if that's true, then what does it say about you? Are you simply an observer of reality? Or are you, in some way, creating it? Schrödinger's cat, a cat that is both dead and alive until observed. You open a box. Inside, there's a cat, or maybe there isn't. Maybe it's alive, maybe it's dead, maybe it's both. The moment you lift the lid, the universe snaps into clarity. But before that, the cat exists in a state of pure uncertainty, alive and dead at the same time, suspended in an eerie limbo of probability. This is Schrödinger's cat, one of the most famous thought experiments in quantum mechanics. It was designed to expose the absurdity of quantum principles when applied to the real world. But instead, it opened a terrifying crack in our understanding of reality. It forced us to ask, is the world waiting for us to observe it before it truly takes form? Here's the setup. Picture a closed box containing a cat, a vial of poison, and a quantum-triggered device. The device is connected to a single radioactive atom, something so tiny that quantum rules dictate its behavior. If this atom decays, it triggers the release of poison, killing the cat. If the atom doesn't decay, the cat remains alive. But here's where things get disturbing. Quantum mechanics tells us that, until measured, the atom exists in a superposition. It has both decayed and not decayed. And because the fate of the cat is tied to the atom, this means that until the box is opened, the cat is also in a superposition. It is both dead and alive, existing in both states simultaneously. Think about what that means. The cat's fate isn't decided until you look. The moment you open the box, reality chooses. Before that, there is no definite outcome, only probability, only a murky cloud of potential existence. And this isn't just some abstract philosophical game. It's an unavoidable consequence of quantum mechanics. In the microscopic world, particles exist in multiple states at once. They are here and there, moving and still, spinning in two directions at the same time. Only when measured, when observed, do they snap into a single, concrete reality. But here's the question that physicists still grapple with. Does this superposition apply to the macroscopic world? If a single atom can exist in multiple states at once, can a cat? Can you? Is reality, at its core, a collection of possible outcomes waiting for an observer to collapse them into certainty? Schrödinger himself wasn't arguing that the cat is literally both dead and alive. He was exposing a fundamental problem with how we interpret quantum mechanics. The experiment forces us to confront a paradox. If quantum laws apply to everything, then a cat, an object we assume is either dead or alive, should also follow these strange rules. But that defies everything we understand about the physical world. And yet, the evidence keeps stacking up. Experiments have shown that particles remain in superposition until measured. In fact, entire molecules, far larger than single particles, have been placed into quantum superpositions, existing in multiple states at once. The more we test the boundaries of this phenomenon, the more reality begins to look like a web of probabilities rather than a fixed, objective structure. So what's really happening inside the box? Some physicists propose the Copenhagen interpretation, which suggests that observation forces reality into a single outcome. The act of looking, of measuring, forces the cat to become either alive or dead. Reality isn't decided until it is witnessed. Others propose an even stranger idea, the many worlds interpretation. This suggests that when you open the box, you don't collapse reality into one outcome. You simply step into the universe where the cat is alive, while another version of you steps into the universe where the cat is dead. Both possibilities exist, but in separate timelines, forever split. And here's where the paradox reaches its most disturbing level. If superposition applies to the cat, then it might also apply to you. Every decision you make, every moment you observe, could be splitting reality into infinite branches, each containing a different version of events. The you who picked up coffee this morning, and the you who didn't. The you who missed a phone call, and the you who answered it. The you who never even existed. Schrödinger's cat forces us to ask a question we may never be able to answer. Does reality exist in a definite form before we observe it? Or is everything just a blur of probabilities, waiting to be resolved by the mere act of looking? Maybe you aren't just an observer in this world. Maybe you are its creator. Wave-particle duality. Light and matter act like both particles and waves. You flick on a light switch. Instantly, photons, the fundamental particles of light, burst from the bulb and scatter across the room. But are they really particles, or are they waves? The answer is both, and neither, and maybe something else entirely. Welcome to the paradox of wave-particle duality, one of the most unsettling discoveries in modern physics. It tells us that light, and even solid matter, can behave as both a particle and a wave, depending on how you look at it. It's as if reality itself is keeping a secret, shifting its nature based on whether you're paying attention. To understand the paradox, you have to go back to a simple yet disturbing experiment, the double-slit experiment, one of the most haunting tests in all of science. Take a beam of light and shine it at a barrier with two slits. What happens if light were just a stream of tiny particles, like tiny bullets? It should pass through one slit or the other and land in two distinct spots on a screen behind the barrier. But that's not what happens. Instead, the light spreads out, bends, and interferes with itself like ripples on a pond, creating a pattern of alternating bright and dark bands. This is wave behavior. Light, it seems, isn't a particle at all. It's a wave, spreading through space, interacting with itself in ways that solid particles never could. But then something strange happens. Scientists decide to measure which slit each photon goes through. The moment they set up a detector to observe the path, the interference pattern disappears. The light now behaves as if it's made of individual particles, forming two distinct bands instead of a wave-like spread. Somehow, the act of observation forces light to behave like particles. But when no one is looking, it acts like a wave. Let that sink in. The way reality behaves changes based on whether it's being observed. When left alone, light moves as a wave, spreading in all directions. The moment we watch it, it decides to behave as tiny, discrete particles. This isn't a glitch or an illusion. It's been tested and confirmed countless times. And the paradox doesn't stop at light. Electrons, tiny particles that make up atoms, also exhibit wave-like behavior. Fire a single electron at a double slit, and it seems to pass through both slits at once, interfering with itself. But measure it, and suddenly it acts like a particle, choosing just one slit. The deeper we dig, the weirder it gets. Everything in existence, electrons, atoms, even entire molecules, can exhibit wave-like behavior under the right conditions. This means that the physical world, the solid, touchable reality you take for granted, might not be as solid as it seems. So what's really happening? Is light a wave or a particle? The unsettling answer is both, and neither. One interpretation is that particles don't have a fixed nature until they're observed. They exist in a state of probability, a blurry superposition of all possible states. The act of measuring collapses this uncertainty into a definite state. In other words, before you look, reality is undefined, a haze of potential outcomes. Another explanation is the many worlds interpretation, which suggests that every possible outcome actually happens, just in separate universes. When a photon chooses to be a particle or a wave, it's not making a decision. It's splitting into different realities, with different versions of the universe evolving in parallel. But here's the real kicker. If observation determines how matter behaves, what does that say about you? Are you simply witnessing reality, or are you shaping it? If an electron doesn't decide whether to be a wave or a particle until it's observed, could reality itself depend on consciousness? Could the entire universe exist in a state of quantum ambiguity, waiting for something, someone, to bring it into focus? Wave-particle duality is more than just a physics problem. It's a challenge to reality itself. It tells us that the fundamental nature of existence is not fixed, not definite, but fluid, shifting based on whether or not it is being watched. And if that's true, then what else about the universe is waiting for you to look before it takes shape? The black hole information paradox. Does information get lost in black holes or not? You're falling faster than anything you've ever imagined. Ahead of you is the event horizon, the point of no return. Behind you, the universe stretches out, still visible, still comprehensible. But once you cross that threshold, everything changes. Space itself twists, time distorts, and all known laws of physics begin to shatter. And then, in an instant, you're gone. No trace of you remains. Not just your body, not just your atoms, but every single piece of information that made you you. It's as if the universe has erased your existence completely, as if you were never here at all. This is the black hole information paradox, a problem that cuts to the core of physics itself. It asks a seemingly simple question: does information get lost in black holes? But to answer that, we first have to understand why black holes are so terrifying, not just as cosmic monsters, but as logical nightmares. According to Einstein's general relativity, a black hole is a one-way trap. Anything that falls in, matter, energy, even light, can never escape. Its gravity is so intense that space itself bends inward, forming a singularity, a point of infinite density where known physics ceases to make sense. But there's a problem. Physics has one golden rule, one principle that has stood the test of time. Information can never be destroyed. Every interaction, every particle, every movement in the universe leaves a mark. Whether you burn a book, dissolve a sugar cube in water, or shred a piece of paper, the information isn't truly lost. It's just rearranged. The laws of physics demand that, at least in principle, you should be able to reconstruct the past from the present. But black holes defy this rule. When something falls into a black hole, all traces of it seem to vanish. The black hole absorbs it, swallows it whole, and leaves no record of what it once was. Two completely different objects, a star, a spaceship, a book, once inside, become indistinguishable. From the outside, all black holes look the same, defined only by their mass, charge, and spin. Everything else, gone. This creates a paradox. If black holes erase information, it means that the universe is fundamentally unpredictable. It means that cause and effect break down. It means that physics itself collapses. And then Stephen Hawking made things even worse. In 1974, Hawking showed that black holes aren't completely black. Due to quantum effects, they slowly leak energy in the form of what is now called Hawking radiation. Over time, this radiation drains the black hole of its mass, causing it to shrink, and eventually disappear altogether. But here's the catch. Hawking radiation carries no information. It's completely random. If the black hole evaporates and disappears, all the information it swallowed is gone forever. The paradox was now unavoidable. If information is lost in black holes, then quantum mechanics, a theory that has never been wrong, must also be broken. But if quantum mechanics is right, then something about our understanding of black holes must be deeply flawed. So where does the information go? Some physicists believe it is somehow preserved inside the black hole, hidden beyond the event horizon. But this doesn't solve the problem. It just delays it. When the black hole evaporates, the information is still lost. Others argue that information escapes, encoded in subtle patterns in Hawking radiation. If true, this would mean that black holes don't destroy information, they just scramble it beyond recognition. But no one has been able to prove exactly how this would work. And then, there's the most radical idea of all, the holographic principle. This suggests that everything inside a black hole is actually encoded on its surface, much like a hologram. If this is true, then information never really enters the black hole at all. It only appears to. Reality itself might be two-dimensional, with the third dimension being a kind of illusion. But the paradox still refuses to die. If information does survive, then where is it? If it doesn't, then is the universe truly as random and chaotic as black holes suggest? The black hole information paradox is more than just an academic puzzle. It's a direct challenge to the fundamental nature of reality. It forces us to confront the most terrifying question of all. Is the universe keeping a record of everything that happens? Or is existence itself capable of forgetting? If black holes truly erase information, then the past is not set in stone. The universe does not remember. And if the universe does not remember, then maybe, just maybe, nothing ever really mattered to begin with. The Fermi Paradox. If the universe is full of planets, where is everyone? You stand outside on a clear night, staring up at the sky. A vast ocean of stars stretches before you, each one potentially surrounded by planets. Logic tells you that at least somewhere out there, on some distant world orbiting a distant sun, intelligent life must exist, and not just exist, thrive. But if that's true, why haven't we seen them? Why hasn't anyone come knocking? This is the Fermi Paradox, one of the most unsettling contradictions in modern science. It asks a simple but haunting question. If the universe is so vast, and if life should be common, then where is everyone? The numbers say we should be surrounded by life. The Milky Way alone contains an estimated 400 billion stars, many of which have planets. With billions of galaxies beyond ours, the number of potentially habitable worlds is staggering. Trillions upon trillions of opportunities for life to emerge. Even if intelligent civilizations are rare, the sheer scale of the universe means that there should still be millions, perhaps billions, of advanced societies. And yet, as far as we know, we are alone. No signals, no visitors, no artifacts drifting through space, just an eerie cosmic silence. So where are they? One possibility is that intelligent life is rare, not just rare, but almost impossibly unlikely. Maybe something about the conditions needed for advanced life is so precise, so delicate, that it happens only once in a billion galaxies. Maybe the great filter, some unknown, unavoidable hurdle, prevents most life from advancing beyond microbes. But then, we exist. We are proof that intelligent life can emerge at least once, so why not twice? Or 1,000 times? Maybe life is common, but intelligent life is self-destructive. If civilizations tend to destroy themselves before they can become interstellar, that would explain the silence. Perhaps the moment a species gains the ability to reach the stars, it also gains the means to annihilate itself. Nuclear war, runaway artificial intelligence, environmental collapse. Perhaps the universe is littered with civilizations that came close, only to burn out before they could spread. Or maybe something else is out there, something that ensures civilizations never make it far enough to be heard. Some have speculated that there could be an unseen force, a cosmic predator that wipes out intelligent species before they can become a threat. Maybe the reason we hear nothing is because the ones who spoke too loudly were silenced. Then there's the zoo hypothesis, the idea that advanced civilizations know about us but are deliberately keeping their distance. Maybe we are an experiment or a protected species, like animals in a wildlife reserve. Maybe the universe is alive with activity, but we are being deliberately shielded from it. Or maybe, just maybe, we are the first. Perhaps life has only recently begun to awaken in the universe, and we are among the first intelligent beings to reach this level of awareness. If this is true, then the great silence isn't a sign of loneliness. It's an invitation, a blank canvas waiting to be painted. The Fermi Paradox forces us to confront one of the deepest existential questions imaginable. Are we alone in the universe? If we are, then life is the rarest and most precious phenomenon in existence. If we aren't, then something huge, is preventing us from seeing our cosmic neighbors. Either answer is terrifying. If we are alone, then the responsibility of life, of intelligence, of everything that makes us us, falls solely on our shoulders. If we are not, then something is keeping us from the others. And until we know what it is, the only thing we can do is stare into the great, silent void and wonder, what's out there, and why hasn't it found us yet? The grandfather paradox. Could you travel back in time and erase your own existence? You step into a time machine. The destination? The past. Specifically, the year your grandfather was a young man, long before your parents were born. You arrive in a world untouched by your existence. Nobody knows you. Nobody suspects what you're about to do. And then you find him, your grandfather, still in his youth, unaware that his future contains a grandchild, you. And in a moment of impulsive madness, or perhaps cold, calculated intent, you eliminate him before he ever meets your grandmother. Then something horrifying happens. Your parents are never born, which means you are never born, which means you never existed to travel back in time in the first place. But if you never traveled back, then your grandfather was never eliminated. He lived, met your grandmother, and your parents were born, leading to you being born, which means you did exist to travel back. Reality loops in on itself, endlessly contradicting its own logic. The timeline shatters, unable to resolve itself. You have created the grandfather paradox, a time travel nightmare where cause and effect begin to cannibalize each other, making existence itself unstable. The paradox exposes the impossible contradictions of time travel. If you could go back and alter the past in a way that prevents your own birth, then how did you ever exist to travel back? If the past can be changed, then time is not a fixed chain of cause and effect. It is something fluid, malleable, but also fundamentally broken. So how do physicists and philosophers deal with this paradox? One idea is that the universe protects itself. Some theorists suggest that time travel to the past might be possible, but only in ways that maintain consistency. No matter what you do, events will always unfold in a way that preserves history. If you try to eliminate your grandfather, something will stop you. Your gun jams, you have a change of heart, or a random accident prevents you from going through with it. The past defends itself, refusing to allow paradoxes to form. This is known as the Novikov self-consistency principle, the idea that time travel can occur, but only in ways that ensure the timeline remains intact. You can interact with the past, but you can never truly change it. But what if you can change the past? Then we run into an even stranger possibility, the many worlds interpretation. In this scenario, the moment you eliminate your grandfather, you don't erase yourself. You simply create a new timeline, one where you were never born. The original timeline, where you did exist, still continues, branching off from the moment of your interference. If this is true, then every action you take in the past spawns an entirely separate reality. The world constantly splits, diverging into infinite versions of history, each one containing a slightly different chain of events. You haven't erased your existence, you've just moved to a timeline where you never existed. Somewhere else, in some other version of reality, the original you still exists, unaware of what has happened. This possibility is deeply unsettling. It means that time is not a single, unified path, but an endless, fracturing tree of possibilities. Every moment, every decision, every alteration of the past doesn't overwrite history. It simply creates another version of it. But if that's true, then what does it say about your reality? Are you on the original timeline, or just one of the infinite branches created by some other traveler's interference? If time is an ever-splitting web of possibilities, is anything truly fixed? Or are you simply one version of yourself among countless others, all playing out different versions of history? The grandfather paradox isn't just a problem for time travelers. It's a challenge to the very nature of reality. It asks whether time is a solid, unchangeable force or a chaotic, ever-diverging storm of possibilities. It forces us to question whether we live in a stable universe or one where the past, present, and future are constantly rewriting themselves. And most disturbingly, it raises a question you may never be able to answer. If you changed the past, would you even know? Or would reality itself shift around you, rewriting history so seamlessly that you'd never realize anything had been altered at all? The Bootstrap Paradox. What if information or objects exist without a clear origin? You're reading a book. It's an old, tattered manuscript filled with ideas that reshape your understanding of the world. Inspired, you copy it word for word and publish it under your own name. The book becomes legendary. Centuries later, an archaeologist uncovers an ancient copy, your copy. But here's the problem. If you only wrote the book because you found it in the past, and it only existed in the past because you wrote it, where did the book originally come from? This is the Bootstrap Paradox, a brain-breaking loop where something, an object, an idea, even a person, appears to exist without ever being created. It has no true origin, no point of invention. It simply exists, caught in an endless cycle, self-generating without ever being made in the first place. And this isn't just a thought experiment. It's a serious paradox in time travel, one that exposes the terrifying instability of cause and effect. Imagine you travel back in time and give Beethoven his own sheet music before he ever composed it. He copies it down, claims it as his own, and history proceeds as normal. But if Beethoven only composed the music because you gave it to him, and you only had it because he composed it, then who actually created it? The paradox suggests that information, or even physical objects, could exist in a causality loop with no definitive beginning or end. It's as if reality itself is skipping a crucial step, the process of creation. And if that's possible, what does it say about the nature of existence? One interpretation is that time is not a linear chain but something self-contained, allowing for loops where cause and effect feed into each other. If information can exist without an origin, then reality might not need a first cause. It could be an infinite cycle, a feedback loop of events perpetuating themselves indefinitely. But this idea challenges one of the most fundamental principles of logic, that everything must have a cause. If something can exist without ever being created, then do we really understand what it means for something to be real? The Bootstrap Paradox isn't just about books or music. It applies to technology, inventions, even people. If a scientist from the future gives Einstein the theory of relativity before he discovers it, and he simply publishes it, then does he truly invent it? If you travel back and become your own grandfather, then where did you originate? And what if the universe itself is caught in such a paradox? Some physicists speculate that the universe might be a self-creating loop, where time folds in on itself and no first cause is necessary. If this is true, then existence isn't something that began. It's something that has always been, an endless cycle without a creator. The paradox forces you to question not just time, but reality itself. If information can exist without an origin, then how do you know anything you've learned, invented, or believed was ever truly created? What if knowledge isn't discovered? It's simply being passed in an infinite loop, never actually originating anywhere. And if that's the case, then the biggest question isn't where did something come from? It's does anything ever truly begin? The twin paradox. One twin on a spaceship. Ages slower than the other on Earth. You and your twin were born seconds apart, two perfect reflections of each other. You share the same memories, the same childhood, the same timeline, until today. Because today, one of you is stepping onto a spaceship, while the other stays behind. Your twin boards a spacecraft capable of traveling at near light speed. You watch as they wave from the window, and then, boom, they're gone, accelerating into the vast emptiness of space. From your perspective, years pass. You grow older, your hair grays, your body weakens. Decades slip by, and then, one day, the ship returns. The door opens, and out steps your twin, young, barely aged at all. They look at you, a stranger now, with decades between you. The two of you were once the same age. Now, you are an old man, and your twin is still young. How is this possible? This is the twin paradox, one of the most mind-bending consequences of Einstein's theory of relativity. It suggests that time is not absolute. It is fluid, bending and stretching depending on how fast you move through space. Here's how it works. According to relativity, time slows down for objects moving close to the speed of light. This phenomenon, known as time dilation, means that while your twin was traveling at near light speed, time for them passed much more slowly compared to you. From their perspective, only a few years passed, but for you, stuck in the normal flow of time on Earth, decades raced by. But here's where the paradox gets tricky. If all motion is relative, can't we flip the perspective? After all, from your twin's point of view, it was you who was moving away at high speed. So shouldn't you be the one who aged more slowly? Shouldn't they return to a world where you are younger? It seems like an impossible contradiction. Both twins should be younger than the other. But reality doesn't allow contradictions. So what's really happening? The resolution lies in acceleration. While your twin was traveling, they experienced something you did not. Extreme acceleration and deceleration. They left Earth, turned around, and came back. This acceleration breaks the symmetry of the situation, making them the one who experiences time dilation, not you. But this opens up even more disturbing questions. If time itself can stretch and contract, then what does that say about aging, memory, and existence? What if someone were to travel at near light speed for thousands of years? To them, only a few moments might pass, while civilizations rise and fall around them. Could time itself be manipulated, paused, extended, or skipped simply by moving fast enough? And if time is relative, then what does that mean for our understanding of reality? We like to think of time as universal, as something that ticks forward at the same rate for everyone, everywhere. But the twin paradox shatters that illusion. It tells us that time is not fixed. It is personal. It flows differently depending on how and where you move. The paradox forces us to ask an unsettling question. Is there such a thing as now? If time is different for everyone, then there is no single present, only an infinite web of shifting perspectives where past, present, and future exist in a strange, ever-changing dance. And if that's true, then what does it mean to grow old, to live a life, to experience time at all? Maybe time is not something we move through. Maybe it's something that moves through us. The arrow of time. Paradox. Why does time move forward? If physics works both ways, you drop a glass. For a brief moment, it hangs in the air. Then, smash, it shatters into dozens of tiny fragments. The pieces scatter across the floor, chaos replacing order in an instant. But now, ask yourself, why doesn't the reverse ever happen? Why don't the shards of glass leap back into place, seamlessly reforming into a perfect, unbroken cup? Why don't waves in the ocean uncrash or smoke return to a cigarette? Why does time, your life, the universe, everything, always march forward and never in reverse? This is the arrow of time paradox, a problem that has haunted physicists for over a century. It reveals a contradiction at the heart of reality. While everything we experience moves in one direction, forward, physics itself doesn't demand that it should. Take Newton's laws of motion, for example. They work equally well whether time runs forward or backward. A planet orbiting a star, reverse time, and the motion still makes perfect sense. Even in Einstein's relativity, time is just another dimension, no different from space. There's nothing in these equations that demands time must flow in one direction. And yet, in your experience, it does. You remember the past, but not the future. You grow older, never younger. Stars burn out. Ice melts. The universe moves toward disorder, never away from it. So what is enforcing time's direction? The answer, physicists suspect, lies in a deep and unsettling law of nature called entropy. Entropy is the measure of disorder in a system. The universe naturally moves from low entropy, order, to high entropy, chaos. A shattered glass is more disordered than a whole one. Smoke dispersed in the air is more disordered than smoke neatly packed in a cigarette. When things break, mix, or decay, they increase entropy, and entropy, it seems, only moves one way. But here's where the paradox deepens. If the laws of physics allow time to move forward or backward equally, why does entropy always increase? Why did the universe start in such a low entropy state, allowing it to unfold into the messy, chaotic cosmos we see today? This question remains unanswered. Some physicists speculate that the Big Bang was a moment of extraordinarily low entropy, a state of pristine order that allowed everything to cascade outward in a one-way progression toward disorder. But why it started that way remains a mystery. Others propose a far more unsettling idea. The past and the future might not be as different as we think. Some interpretations suggest that if we could somehow perceive reality from the right perspective, we might see time flowing both ways at once, our experience of forward being just a trick of perception. But the paradox forces us to ask an even deeper question. If time only flows forward because of entropy, then is our perception of reality merely the result of increasing disorder? And if so, then what happens when entropy reaches its maximum? Does time itself grind to a halt, or does it somehow impossibly reverse? The arrow of time paradox reminds us that the universe should be symmetrical, but somehow it isn't. It whispers the possibility that our understanding of time is incomplete, that the very fabric of reality holds secrets about time's true nature that we have yet to uncover. And it leaves us with a final, disturbing thought. If time is only an illusion of entropy, then what does that say about everything we have ever known, felt, or remembered? The Cosmic Horizon Paradox. How can the universe be infinite but have an observable edge? You stand under a vast night sky, staring into the abyss of space. The universe stretches in all directions, endless, immeasurable, and yet, Scientists tell you there's a limit to what you can see, a cosmic horizon beyond which nothing is visible, as if the universe has an edge. But how can that be? If the universe is infinite, shouldn't you be able to see forever? Shouldn't light from the most distant galaxies eventually reach your eyes? This is the Cosmic Horizon Paradox, a contradiction at the heart of cosmology. It forces us to confront an unsettling truth. The universe may be infinite, but we are trapped within a finite bubble of perception. To understand why, you need to go back to the speed of light, the ultimate speed limit of reality. Light from distant galaxies takes time to reach us, traveling across the void at 300,000 kilometers per second. But here's the problem. The universe itself is expanding. And it's not just expanding, it's accelerating, stretching space itself at a rate that outpaces even light. As a result, there are distant regions of the universe from which light will never reach us. No matter how long we wait, those galaxies are moving away faster than their light can travel. They are beyond our cosmic horizon, forever cut off from view. But here's where the paradox emerges. If the universe is truly infinite, then shouldn't it contain an infinite number of galaxies? And if so, shouldn't at least some of their light eventually reach us, given infinite time? If the universe has no end, then why does our vision of it have one? One possible explanation is that the observable universe is not the full universe. What we see is only a fragment, a small, shrinking island within an infinite cosmic ocean. The universe may extend far beyond our cosmic horizon, but those regions are permanently lost to us. But this leads to a disturbing implication. If we can never interact with those distant parts of the universe, do they really exist in any meaningful way? If something is beyond all possible measurement, beyond even the theoretical ability to observe it, does it have any more reality than a thought, an idea, a dream? Some scientists take the paradox further, suggesting that the cosmic horizon might not just limit what we can see, but what we can affect. If no information can travel beyond the horizon, then we are effectively cut off from the rest of the cosmos. The universe could contain other galaxies, other civilizations, even entire other versions of ourselves, but we will never know. And here's the most unsettling possibility. What if our own universe is just a bubble inside something much larger? What if what we see as the entire cosmos is just a tiny pocket of a far greater reality, a speck in an infinite multiverse, each pocket hidden from the others behind their own unreachable horizons? The Cosmic Horizon Paradox forces us to confront a terrifying limit, not just of our sight, but of our understanding. It suggests that reality itself might be bigger than anything we can ever know. That no matter how far we travel, how much we learn, there will always be something beyond, hidden, unreachable, lost in the accelerating expansion of space. And perhaps the greatest paradox of all is this. If we can never observe what lies beyond the cosmic horizon, how can we ever be sure that we're not the only thing that exists? What if, beyond that edge, there is nothing? Zeno's paradoxes. Can you ever truly reach your destination? You take a step forward, then another. You are walking toward a destination, a door, a finish line, a goal in the distance. You are certain that with enough time, you will get there. But what if you never do? What if no matter how far you travel, you are always halfway there? This is the disturbing logic behind Zeno's paradoxes, a collection of thought experiments that challenge the very idea of motion itself. They suggest that, in theory, reaching any destination should be impossible. The most famous of these paradoxes is the dichotomy paradox. It goes like this. Before you can reach your destination, you must first reach the halfway point. Then, to cover the remaining distance, you must first get halfway again, then halfway again. and again, and again, forever. At every moment, you are only ever covering half the remaining distance, and since this process never truly ends, the paradox suggests that you can never actually arrive. You will always be infinitely close, but never quite there. But wait, you might say, people reach destinations all the time. You walk across the room, finish a race, drive across town. Clearly, motion works, so where's the flaw? Here's the problem. Math and reality seem to disagree. Zeno's paradoxes expose a deep contradiction between logic and experience. Mathematically, dividing distance into infinite halves suggests that motion should require completing an infinite number of steps, and completing an infinite number of anything should take an infinite amount of time. Yet, in reality, you reach your destination just fine. How can that be? One possible resolution lies in converging series, the idea that an infinite number of steps can still add up to a finite result. Each step takes less time than the one before, shrinking so rapidly that the total time required remains finite. But this doesn't fully resolve the paradox, because it raises a deeper question. How does motion even happen in a universe that can be infinitely divided? If space and time are continuous, meaning they can be broken down into smaller and smaller pieces forever, then motion should still be an infinite process. But if space and time are not continuous, if there is some fundamental smallest unit beyond which you cannot divide, then what does that mean for our understanding of reality? The implications of Zeno's paradoxes don't stop at motion. They hint at a deeper, hidden structure of the universe itself. Is space truly continuous, or is it made of tiny, indivisible units, like pixels on a screen? Does time flow smoothly, or does it jump in discrete steps, like frames in a movie? And if motion is just an illusion created by these quantum jumps, then what does that say about free will, cause and effect, and even time itself? Zeno's paradoxes remind us that even the simplest, most unquestioned aspects of reality, like moving from one point to another, can unravel under deep scrutiny. They suggest that the universe is either infinitely divisible, making motion an impossible riddle, or fundamentally quantized, revealing a hidden, step-like nature to time and space. Either way, the paradox remains. And the next time you take a step forward, ask yourself, did you really move at all? Or are you just infinitely close to where you thought you were going? The infinite hotel paradox. A hotel with infinite rooms is always full, yet always has space. You arrive at a hotel after a long journey. The glowing sign outside reads, Hilbert's Infinite Hotel. The lobby is grand, stretching endlessly in both directions. You approach the front desk and ask for a room. I'm sorry, the clerk says, but we're completely full. Your heart sinks. Every single room, room 1, room 2, room 3, stretching infinitely, is occupied. But then, the clerk smiles. Luckily, we can still make space for you. He picks up the phone and issues a strange request. Every guest, please move to the next room. The guest in room 1 moves to room 2. The guest in room 2 moves to room 3, and so on. Since there is no final room, this process never runs out of space. Just like that, room 1 becomes vacant, and you have a place to stay. Welcome to the Infinite Hotel Paradox, a mind-bending thought experiment from mathematician David Hilbert that exposes the strange, counterintuitive nature of infinity. It forces you to confront the bizarre reality that something can be completely full, yet still have space for more. But the paradox doesn't stop there. Imagine that, instead of just you, an infinite number of new guests arrive at once, each hoping for a room. The clerk doesn't panic. He simply issues a new command. Every guest, please move to the room number that is twice their current number. The guest in room 1 moves to room 2. The guest in room 2 moves to room 4. The guest in room 3 moves to room R. Now, all the odd-numbered rooms, room 1, room 3, room 5, are vacant, providing infinite space for the infinite newcomers. This is the bizarre nature of infinity. It behaves in ways that defy logic. You would think that if something is full, it cannot hold more. But in an infinite system, adding more does not necessarily mean running out of space. This paradox reveals a troubling truth. Our intuition about numbers, space, and reality completely breaks down when we deal with the infinite. And here's where things get even stranger. Imagine that every guest checks out at the same time. The hotel should now be empty, right? But if a new guest arrives and asks for a room, the clerk can say, "Well, our hotel is infinite, so there is still an infinite number of rooms. Please take room 1. Even after subtracting infinity, the hotel is still infinite. And what if, instead of checking out, every guest disappears except for the ones in the even-numbered rooms? Now, half the original guests are gone, but the hotel still has an infinite number of people inside. Infinity divided by 2 is still infinity. This paradox exposes a profound flaw in our understanding of numbers. Infinity is not like normal counting. In an infinite system, subtraction, multiplication, and division do not behave the way they do with finite numbers. But here's the truly disturbing question. Does infinity exist in reality? If space is infinite, does that mean the universe can always fit more galaxies, more stars, more matter? If time is infinite, does that mean there was no real beginning and that there will never be an end? And if you exist in an infinite reality, are there infinite versions of you, each living slightly different lives in slightly different circumstances? The infinite hotel paradox doesn't just challenge mathematics, it challenges our very concept of reality. It suggests that the universe might be far stranger than we can ever comprehend, where infinity isn't just a number, but a fundamental feature of existence. And if that's true, then maybe the real question isn't how much space exists, but whether the concept of space itself even makes sense in an infinite world. Banach-Tarski Paradox. A sphere can be split into pieces and reassembled into 2 identical spheres. You hold a perfect sphere in your hands. Maybe it's a baseball, a pearl, or even a planet. It's a single, solid object, whole, unbreakable, finite. But what if I told you that, without adding or removing anything, you could split it apart and end up with 2 identical spheres exactly the same size as the original? It sounds impossible. It should be impossible. And yet, mathematics says it's true. This is the Banach-Tarski Paradox, a theorem in set theory that completely breaks our understanding of space, volume, and reality itself. It states that, using only a series of mathematical cuts and rotations, you can take a single sphere, divide it into 5 pieces, rearrange those pieces, and suddenly, out of nowhere, you have 2 spheres, exactly the same size as the first. No stretching, no duplication, no extra material, just infinity at work. So how does this paradox work? The trick lies in the nature of infinity and uncountability. In the normal, everyday world, cutting something in half gives you 2 smaller halves. That's how physical matter behaves. But in the world of pure mathematics, objects are not made of atoms. They are made of points, and points are infinitely divisible. The pieces in the Banach-Tarski paradox aren't normal slices like you'd get from cutting a cake. Instead, they are fractured, broken down into infinitely complex, non-measurable sets of points that are scattered in such a way that they defy traditional geometry. Because of this, these pieces can be rearranged in a way that doubles the original shape. To be clear, this doesn't work in the real world. It relies on the assumption that space is infinitely divisible with no smallest unit of measurement. In reality, physical matter is made of atoms, and atoms cannot be split into an infinite number of points. But mathematically, there is no smallest unit of space, and if space is truly continuous, then theoretically, the Banach-Tarski Paradox applies to the real universe. So what does this mean? It suggests that our intuitive ideas about volume, size, and conservation of matter might be illusions, concepts that only hold up at the human scale, but break apart when examined under the lens of infinity. It forces us to ask, is space itself infinitely divisible? If so, then what we call solid objects might be nothing more than convenient approximations. Can infinity exist in the physical world? If reality follows strict conservation laws, then Banach-Tarski should be impossible. But if the universe is built on pure mathematics, then maybe, just maybe, it isn't. Could reality itself be reassembled like the paradox suggests? If space can be reshuffled at an infinite level, does that mean reality can be taken apart and put back together differently without breaking any fundamental rules? The Banach-Tarski Paradox forces us to confront an unsettling truth. The laws that govern our experience of the world may not be the same laws that govern reality itself. And if that's true, then how much of what you believe about space, matter, and even existence is just an illusion created by your mind's inability to comprehend the infinite? Russell's Paradox. Does a set of all sets that don't contain themselves contain itself? You're organizing a list, a master catalog of every possible list that doesn't include itself. Simple enough, right? Every normal list that follows this rule gets written down. But then you come to a final question, one that shatters the entire system. Should you include this very list on the list? If you do, then it does contain itself, which means it shouldn't be on the list. But if you don't include it, then it doesn't contain itself, which means it should be on the list. And just like that, logic collapses in on itself. This is Russell's Paradox, discovered by philosopher and mathematician Bertrand Russell in 1901. It seems simple, a problem of sorting sets into categories, but it shook the very foundations of mathematics, exposing a contradiction so deep that it threatened to destroy the entire system of logic on which numbers, equations, and formal proofs are built. To understand the paradox, imagine a town with a peculiar rule. There is a barber who shaves everyone who does not shave themselves. Now ask, who shaves the barber? If the barber shaves himself, then he shouldn't, because he only shaves people who don't shave themselves. But if he doesn't shave himself, then by the rule, he must shave himself. It's an impossible loop. Russell's paradox is the mathematical version of this paradox. It asks, does the set of all sets that don't contain themselves contain itself? If it does contain itself, then it shouldn't, because it only includes sets that don't contain themselves. If it doesn't contain itself, then it should, because it fits the rule of containing all sets that don't contain themselves. There is no escape. The paradox exposes a fundamental contradiction within set theory, the branch of mathematics that defines how we organize numbers and objects, and the implications are terrifying. Before Russell, mathematicians believed that sets were a simple, reliable way to build the foundations of logic. Numbers, geometry, even reality itself, everything seemed to rest on a clear, structured hierarchy of sets. But this paradox revealed a deep, hidden flaw, a contradiction buried at the heart of formal mathematics. If a system of logic could create contradictions, then could it truly be trusted? Russell's paradox sparked a crisis. Mathematicians scrambled to rewrite the very foundations of their field. Some tried to patch the system by creating new rules, like limiting what kinds of sets were allowed to exist. Others, like Gödel, took the paradox even further, proving that any sufficiently complex system of logic will always contain unresolvable contradictions. This raises an unsettling question. Is mathematics truly real, or is it just a fragile invention full of hidden paradoxes? If numbers themselves rely on a system that can collapse into contradiction, then what about reality? Could existence itself contain logical errors, paradoxes buried so deeply that we simply haven't noticed them yet? Russell's paradox isn't just a mathematical puzzle, it's a glitch in logic itself. It suggests that even our most fundamental systems of reasoning may not be as airtight as we assume. And if paradoxes lurk at the core of logic, how many more are hiding in the fabric of reality itself? The liar paradox. This statement is false. Is it true or false? You read a simple sentence, "This statement is false." And then, suddenly, your mind crashes. If the statement is true, then what it says must be correct, meaning it is false. But if it's false, then what it says is incorrect, meaning it must be true. You're caught in an endless loop, a logical black hole that refuses to resolve. This is the liar paradox, one of the simplest yet most disturbing contradictions in logic. It should be answerable, but it isn't. It's not just a linguistic trick. This paradox breaks the fundamental rules of truth itself. Normally, a statement is either true or false. There is no in-between. But the liar sentence refuses to fit. It exists in a strange, impossible limbo, like a glitch in reality that logic can't resolve. And here's where things get worse. The liar paradox isn't just an isolated puzzle, it's a virus that infects logic itself. Imagine a variation. Everything I say is false. If this statement is true, then everything the speaker says is false, including that very sentence. But if it's false, then at least some things the speaker says must be true, which contradicts the original statement. Or take a more insidious version. This sentence is not provable. This one is far more dangerous. If the sentence is true, then it cannot be proven. But if it cannot be proven, then we have just proven it, meaning it must be false. This led mathematician Kurt Gödel to one of the most earth-shattering discoveries in the history of mathematics, his incompleteness theorems, which prove that in any sufficiently complex system of logic, there will always be true statements that cannot be proven. Yes, logic itself has limits, but how deep does the paradox go? If truth and falsehood can collapse into paradox, what does that mean for knowledge, reality, even consciousness itself? Could the universe contain statements that are neither true nor false, but both? If reality is governed by logic, and logic contains paradoxes, then is existence itself built on contradictions? Or is the liar paradox proof that our understanding of truth is fundamentally flawed? For centuries, philosophers and logicians have tried to escape this loop. Some argue that truth must come in degrees, allowing for statements that are partially true and partially false. Others suggest that language itself is the problem. Perhaps statements can refer to themselves in ways that reality simply does not allow. And yet, the paradox refuses to die. It lurks in every system of thought, waiting for the right moment to unravel certainty. It whispers the terrifying possibility that logic is not a perfect machine, but a fragile, inconsistent framework, full of holes we are only just beginning to see. So now, look again at the sentence. This statement is false. You understand it. You see the paradox, and yet you cannot resolve it. Maybe the real question isn't, is it true or false? Maybe the real question is, can anything be truly known at all? The missing dollar paradox. Where did the missing dollar go? 3 friends walk into a hotel and decide to share a room. The receptionist tells them the price is $30, so they each contribute $10. handing over a total of $30. Later, the hotel manager realizes there was a mistake. The room only costs $25. He gives $5 to the bellboy and tells him to return it to the three friends. But the bellboy, being sneaky, decides to keep $2 for himself. He gives $1 back to each friend, meaning each person ends up paying only $9 instead of $10. Now let's do the math. Each friend paid $9. 3 times $9 equals $27. The bellboy kept $2. That brings the total to $27 plus $2 equals $29. But wait, they originally paid $30. Where did the missing dollar go? This is the missing dollar paradox, a seemingly simple puzzle that exposes a flaw in the way our minds process numbers. The paradox tricks you into thinking that there is a missing dollar, but in reality, it's just a misdirection of logic. The confusion arises because we're adding numbers that shouldn't be added together. When we say each friend paid $9 and the bellboy kept $2, we are mixing different parts of the transaction. The $27 already includes the $2 stolen by the bellboy, so adding it again creates an illusion of an extra missing dollar. The correct breakdown is this. The friends originally paid $30. The hotel kept $25. The bellboy kept $2. The friends got back $3. Total, $25 plus $2 plus $3 equals $30. No money is missing. So why does the paradox work? Because our brains expect numbers to balance in a simple way, and when they don't, we instinctively assume something is missing. The trick lies in forcing you to add a number when you should actually be subtracting. But the real paradox isn't about the missing dollar. It's about how easily our perception of logic and reality can be manipulated. If such a simple math problem can distort our reasoning, what else in the world might not be as straightforward as it seems? The missing dollar paradox reminds us that even simple truths can be deceptive, and sometimes the greatest illusion isn't what's missing, but what we think we see. The Monty Paradox. Changing your choice in a game show doubles your chance of winning. You're on a game show. The grand prize? A brand new car. The host, Monty Hall, stands before you with 3 closed doors. Behind one of them is the car. Behind the other 2? Goats, worthless, at least in terms of the game. You pick a door, let's say door number 1. Monty, who knows what's behind each door, doesn't immediately reveal whether you've won. Instead, he does something tricky. He opens one of the other 2 doors, revealing a goat. Now, you're left with 2 doors, the one you originally picked and the remaining unopened door. Then Monty offers you a choice. Stick with your original door or switch to the other one. Your instincts scream at you to stay put. After all, you had a 1 in 3 chance at the beginning, and now there are only 2 doors left. Shouldn't it be 50-50? Number switching actually doubles your chances of winning. This is the Monty Paradox, one of the most counterintuitive and frustrating puzzles in probability theory. At first glance, it seems like common sense. After Monty reveals a goat, there are 2 doors left, so your odds should be 50-50. But this thinking is a trap. Let's break it down. When you first picked a door, the odds were 1/3 chance you picked the car, 2/3 chance you picked a goat. Now Monty knows what's behind each door, so he will always open a door with a goat. This is the crucial part. The fact that he opens a door does not change the fact that you originally had a 1 in 3 chance of picking the car. But here's the trick. If you originally picked the car, 1/3 chance, switching loses. If you originally picked a goat, 2/3 chance, Monty's action has essentially filtered out the bad choice, and switching wins. Since you originally had a 2/3 chance of picking a goat, that means switching gives you a 2/3 chance of winning the car, double the odds of staying. Still skeptical? Imagine playing this game 100 times. If you always stay, you'll win about 33 times, since you started with a 1/3 chance of picking the car. If you always switch, you'll win about 66 times, since you started with a 2/3 chance of picking a goat, which means Monty's reveal has helped you. It doesn't just feel counterintuitive, it is counterintuitive. But probability isn't about feelings. It's about logic. The Monty Paradox is a perfect example of how human intuition struggles with probability. It exposes a flaw in how we naturally think about uncertainty. We assume that eliminating an option reshuffles the odds evenly, but it doesn't. The probabilities are set from the moment we choose, and this paradox goes beyond game shows. It applies to decision-making, risk assessment, and even real-world scenarios where we mistake our perception of odds for reality. It teaches us that sometimes the best move is the one that feels wrong. So next time you're faced with a tough choice, ask yourself, are you sticking with your first instinct out of comfort? Or is there a better move hidden in the logic of the situation? Because in the Monty Hall game, and in life, switching just might be the smarter choice. Gödel's Incompleteness Theorem. No system of logic can prove all truths within itself. You believe that mathematics, the foundation of logic, science, and the very structure of reality, is complete, that every mathematical truth can be discovered, proven, and made certain, that within a well-defined system of rules, everything that is true can be logically proven to be true. But what if that belief is wrong? What if, hidden within the core of logic itself, is an inescapable flaw? This is Gödel's Incompleteness Theorem, a discovery by the Austrian logician Kurt Gödel in 1931 that sent shockwaves through mathematics and philosophy. It proved something unsettling. Any sufficiently complex system of logic is either incomplete or inconsistent. In other words, within any system capable of basic arithmetic, there will always be true statements that cannot be proven within that system. There will always be truths that are unreachable, forever out of logical grasp. And worse, if a system were somehow able to prove all truths, it would also be capable of proving contradictions, making it completely unreliable. Mathematics, once thought to be the perfect, unshakable foundation of certainty, is fundamentally incomplete. But how could Gödel prove this? His argument was pure genius. He devised a way for a mathematical system to talk about itself, creating a statement that essentially says, this statement cannot be proven. Now, think about the implications. If this statement is true, then it means exactly what it says. It cannot be proven within the system. The system is incomplete. But if the system could prove the statement, then it would be false, meaning the system has proven something untrue, making it inconsistent. There is no escape. Any system that tries to prove everything will eventually contradict itself. Any system that avoids contradictions will leave some truths forever unprovable. And so, certainty dies. The implications of Gödel's theorem reach far beyond mathematics. It suggests that no formal system of rules, whether logic, science, or even language, can ever be truly complete. There will always be questions that cannot be answered from within the system itself. And that raises a disturbing thought. If no system can fully explain itself, then can the universe ever be fully explained from within the universe? Could reality itself be incomplete, full of truths that will forever remain beyond our reach? Even more unsettling, Gödel's theorem suggests that even the human mind might be bound by these limits. We like to believe that reason can uncover all truths, that intelligence can eventually answer every question. But if mathematics, the most precise system we have, is incomplete, then what does that say about our own ability to understand the deepest truths of existence? The theorem forces us to confront an unsettling paradox. There are truths that exist, but we may never have the power to prove them. Reality itself may contain mysteries that cannot be solved, not because we lack intelligence, but because the very nature of logic forbids it. And so, Gödel's incompleteness theorem leaves us with a chilling possibility. What if some of the most important truths about existence will always remain unknowable? The infinite monkey theorem. Given enough time, monkeys typing randomly would write Shakespeare. A monkey sits in front of a typewriter. It has no understanding of language, no concept of words, no intention of writing anything meaningful. It simply hits keys at random, over and over again. At first, the results are nothing but gibberish, meaningless strings of letters, numbers, and punctuation. But now, imagine infinite monkeys on infinite typewriters, typing endlessly for infinite time. Given enough time, one of them, purely by chance, will eventually type out the complete works of Shakespeare, word for word, comma for comma, perfectly. This is the infinite monkey theorem, a paradox that reveals the mind-bending implications of infinity and probability. It suggests that pure randomness, if given unlimited attempts, can recreate anything. At first, it sounds ridiculous. How could random typing ever produce something as intricate, as intentional, as Hamlet? But mathematically, it's inevitable. The reason? Probability does not care about meaning. Imagine trying to type just one phrase, to be or not to be. If you type completely at random, the odds of getting this exact phrase in one try are astronomically low. But now, what if you had infinite tries? If the monkeys type forever, then at some point, every possible combination of letters must occur. That means that somewhere, buried in the chaos of random keystrokes, is not just Shakespeare, but every book ever written, every speech ever given, every thought ever recorded. Even the story of your own life, written in perfect detail, already exists, just waiting to be randomly typed. But here's where the paradox deepens. While infinity guarantees that everything will eventually be typed, it also guarantees that almost all of it will be meaningless nonsense. The vast, overwhelming majority of what is written will be unreadable chaos, endless sequences of letters that mean nothing. And this raises a disturbing question. Does meaning exist in a universe governed by randomness? If pure chance is capable of producing Hamlet, then what separates randomness from intentional creation? If the difference between nonsense and genius is just time and probability, then is anything truly meaningful, or is meaning just an illusion we impose on the randomness of reality? Some scientists have drawn eerie parallels between the infinite monkey theorem and the nature of the universe itself. The laws of physics suggest that our own existence is the result of a long chain of probabilities. Given enough time, could the universe have randomly typed the conditions necessary for life? Could intelligence itself be the product of infinite cosmic randomness, refined through selection, rather than something inherently special? Or take it one step further, if the universe is truly infinite, then right now, somewhere in the vast cosmic expanse, there must exist another version of you, another Earth, another history, another reality identical to this one, simply because infinity demands it. The infinite monkey theorem is not just a paradox of probability, it is a philosophical nightmare. It forces us to confront the unsettling idea that anything that can happen will happen, eventually. It means that given infinite time, we are not unique, that nothing is impossible, that every event, no matter how unlikely, has already happened somewhere and will happen again. And perhaps the most unsettling idea of all, if randomness is truly infinite, then somewhere out there, right now, a monkey is already typing this sentence. Newcomb's paradox. Can perfect prediction render free will meaningless? You walk into a room. In front of you sit two boxes. Box A is transparent and contains $1,000. Box B is opaque and its contents are unknown. A mysterious being, let's call it the predictor, has already decided what's in box B before you even entered the room. This being is not just intelligent, it is perfectly accurate. It knows your mind better than you do. Now you have a choice. 1. Take both boxes, A plus B. 2. Take only box B. But here's the catch. If the predictor predicted you would take both boxes, then it left box B empty. If the predictor predicted you would take only box B, then it put $1 million inside it. You stand there, sweating. What do? Your rational mind argues, box B is already full or empty. The predictor made its choice in the past, so it doesn't matter what I do now. The best option is to take both boxes, because I'll get either $1,000 or $1,001,000. But then another thought creeps in. Wait, if the predictor is truly perfect, then it already knows what I'll do. If I take both boxes, it must have foreseen that, meaning box B is empty. The only way to guarantee I get the million is to take only box B. And here's where the paradox destroys your concept of free will. If the predictor is truly infallible, then your choice isn't really a choice at all. It was already decided. You are merely acting out a script that was written before you even stepped into the room. But if you truly have free will, then the predictor can't be perfect, because you could surprise it by making a different choice. So which is it? This is Newcomb's paradox, a mind-shattering dilemma that forces you to confront the tension between free will and determinism. It asks, if a being can perfectly predict your choices, do you really have a choice? If you do have free will, doesn't that mean the predictor can't be perfect? And if the predictor is perfect, then isn't your sense of making a decision just an illusion? This paradox shakes the very foundation of agency, control, and reality itself. If the predictor exists in the real world, say as an advanced AI, a godlike entity, or even the laws of physics, then everything you do has already been determined. Your thoughts, actions, and choices are merely the unfolding of a script written by a force beyond your control. But if true free will exists, then the universe cannot be perfectly predictable. There must be some randomness, some fundamental unpredictability that allows you to act outside of fate. And here's where the paradox deepens. In real-world experiments, people who choose only box B tend to walk away richer. The reasoning is simple. Those who trust the predictor's accuracy and commit to one box are the ones it fills with $1 million. Those who try to outthink it are the ones it outthinks, which means maybe the illusion of free will is necessary for the paradox to function. Maybe the moment you believe you have a choice, the predictor has already won. So now, the question is yours. Do you take both boxes clinging to logic and control, or do you take only box B, surrendering to a destiny that was decided before you even knew you had a choice? And if the predictor is watching you right now, did you ever have a choice at all? The ship of Theseus paradox. If you replace every part of a ship, is it still the same ship? A great wooden ship, sailed by the legendary hero Theseus, rests in a harbor. Over time, its planks begin to rot. Slowly, piece by piece, the shipwrights replace each wooden board, ensuring it remains seaworthy. Years pass. Every single plank, mast, and sail has been replaced. Not a single original part remains, and yet it still stands there, proudly floating in the harbor. Now, stop and ask yourself, is it still the ship of Theseus? At first, the answer seems obvious. Yes, of course it is. The ship never disappeared. It was simply maintained. The identity of the ship doesn't come from its parts, but from the fact that it has continuously existed as Theseus' ship. But what if we take this further? Imagine that the original planks were not thrown away, but instead collected and reassembled in another dock. Now, there are two ships. One, the one in the harbor, made entirely of new parts. Two, the one built from the old parts, identical to the original. Now comes the paradox. Which one is the real ship of Theseus? Is it the one that was continuously maintained, even though it has none of its original parts? Or is it the one built from the original materials, even though it was reconstructed from scratch? The paradox exposes a fundamental problem with identity. Does something remain the same thing because of continuity or because of its original components? And this isn't just about ships. If every cell in your body is gradually replaced over time, which it is, are you still the same person you were years ago? If a beloved childhood toy has been entirely repaired and restored, is it still the same toy or just a replica? If a song is covered by a new artist, note for note, does it retain its original essence or is it something entirely new? And the paradox deepens even further. If you were gradually replaced, if your thoughts, memories, and personality evolved to the point where none of your original identity remained, are you still you? Philosophers have debated this for centuries, and the paradox offers two opposing views of identity. 1. The continuity theory. Identity persists through time and function, even if all physical components are replaced. The ship of Theseus is the same ship because it was continuously Theseus's ship. You are still you because your consciousness remains uninterrupted. 2. The materialist theory. Identity is tied to the physical parts. If all the original components are replaced, then the ship is no longer the same. Likewise, if your memories and personality were erased and replaced, you would no longer be the same person. And now, let's take this to an extreme. If we copied your mind, thought by thought, and uploaded it into a machine, would that still be you? If a perfect clone was made of you, indistinguishable in every way, which version would be the real you, or would both be? The ship of Theseus. Paradox forces you to confront a chilling realization. Identity is not as simple as it seems. Whether it's a ship, a person, or an idea, the question of what makes something itself is far more complex than we like to believe. And maybe, just maybe, the only answer is this: identity is not a fixed thing. It is a story we choose to tell. The brain in a vat. How do you know you're not just a brain? Connected to a simulation. Right now, you feel the weight of your body. You see the world around you, light, color, movement. You hear sounds, maybe the hum of distant traffic, the tapping of your fingers on a surface. You feel real. You feel alive. But what if it's all an illusion? What if your body doesn't exist? What if everything you see, hear, touch, and remember is nothing more than a simulation fed directly into your brain? This is the brain in a vat paradox, a modern twist on the age-old question. How do you know reality is real? Imagine a scenario. Scientists remove your brain from your body and place it in a vat of life-sustaining fluid. Electrodes are attached to your neurons, perfectly simulating every experience you would normally have. You see a world, you feel things, you think you're still you, but in reality, you're just a disembodied brain receiving electrical signals designed to create the illusion of a full life. Now the real problem? How would you ever know? Every experience you've ever had, your memories, your sensations, your very thoughts, are just electrical signals interpreted by your brain. But if those signals could be manipulated perfectly, then there would be no difference between reality and simulation. You could have lived your entire life inside an illusion, and you would never have any way of proving otherwise. And this isn't just science fiction. The paradox shakes the very foundation of knowledge itself. We assume we can trust our senses, but what if we can't? How can you be certain that anything you perceive exists outside your own mind? Philosophers like René Descartes wrestled with this centuries ago. He asked, what if an evil demon was deceiving me, fabricating my entire reality? His solution, I think, therefore I am, suggested that even if everything was an illusion, at least the thinking self must exist. But does that actually solve the problem? Even if you are thinking, that doesn't prove what you are or where you are. Are you a human in a real world? A brain in a vat? A character in some higher dimensional being's dream? A simulated mind running on an advanced supercomputer? And here's where the paradox deepens. If you were just a brain in a vat or a simulation inside some cosmic machine, would it even matter? If every thought, every experience, every relationship feels real, then what is the difference between reality and illusion? If you could never wake up from the simulation, then isn't that your reality? And if reality is indistinguishable from illusion, then does it even make sense to call it an illusion at all? This paradox has profound implications, especially in an age where virtual reality, artificial intelligence, and neural interfaces are becoming increasingly advanced. If we could simulate consciousness inside a machine, what would stop us from creating entire simulated universes? And if that's possible, how do you know you're not already in one? Perhaps you are just a program running inside an inconceivably advanced civilization's experiment. Perhaps your memories were loaded into you just moments ago. Perhaps there is no real world, just an infinite series of simulated realities stacked within each other like Russian dolls. The brain in a vat paradox isn't just about skepticism, it's about the limits of human knowledge. It forces us to ask, can we ever prove that reality is real? If we can't tell the difference, does it matter? And if this world isn't real, what is waiting for us outside of it? Or maybe there is no outside. Maybe the only thing that exists is you. The Teletransportation Paradox. If a teleportation device copies and reassembles you, is it still you? You step into the teleportation pod. A gentle hum fills the air as the machine scans your body. Every atom, every neuron, every synapse. Instantly, it vaporizes you, reducing your body to pure energy. 1,000 miles away, in another teleportation chamber, a new version of you appears. Every single particle is reconstructed exactly as it was. Your memories, thoughts, and personality remain intact. You step out, completely unaware that anything has happened. But stop. Ask yourself, is that really you? Or did the original die, and a perfect copy, indistinguishable but entirely separate, take your place? This is the Teletransportation Paradox, a disturbing question that challenges our very definition of identity. It forces you to ask, what makes you, you? At first, it seems clear. If every atom is reconstructed exactly the same, and if your consciousness feels unbroken, then you must still be you, right? But what if something went wrong? Imagine that, due to a glitch, the original wasn't destroyed, and now there are two of you, one standing in the original pod, the other in the destination chamber. Both have your memories. Both think they are you, but they can't both be you, can they? So which one is real? And if the original was vaporized, then was that death? Was the teleported version merely a copy, a lifeless replica with your memories, believing itself to be you? Or does you only exist as a pattern, something that can be recreated, as long as the structure remains the same? This paradox raises an unsettling question about personal identity. Are you your physical body? If so, then teleportation kills you and replaces you with a clone. Are you your memories and consciousness? If so, then teleportation doesn't matter. As long as the copy thinks and remembers exactly like you, it is you. But what if you are something more? What if there is something beyond physical structure? Some kind of essence, a soul, that cannot be copied? If that's true, then teleportation is not just travel, it's an execution followed by a fabrication. And here's where the paradox deepens. If teleportation is death, then what about everyday life? Your body is constantly changing, cells die and are replaced, memories shift, thoughts evolve. The atoms that make up your body today are not the same ones you had years ago, yet you still feel like you. If you can survive the gradual replacement of your body over time, why wouldn't you survive instantaneous replacement through teleportation? And if teleportation is just a faster version of what already happens to you every day, then maybe the fear is misplaced. Maybe you are nothing but a constantly updating pattern of information, a story being rewritten with every moment. Or maybe every time you step into that teleportation machine, you die, and someone else, someone who thinks they are you, steps out. The paradox forces you to ask, what if you have already died 1,000 times, your body changing, your thoughts shifting, while something new continues to believe it is you? And if that's true, have you ever truly existed at all? Boltzmann brain paradox. What if your consciousness is just a random fluctuation of the universe? Right now, you are thinking, you are aware, you feel real. But what if that feeling is a lie? What if, instead of being a human in a vast, structured universe, you are just a momentary accident, a fleeting, self-aware bubble of randomness floating in an infinite void? This is the Boltzmann brain paradox, a terrifying thought experiment that suggests your very existence might be an illusion, nothing more than a cosmic glitch. To understand it, we have to talk about entropy, the natural tendency of the universe to move toward disorder. Over time, stars burn out, galaxies drift apart, and the universe decays into a vast, cold emptiness. But in an infinite universe, even the most improbable events will eventually happen. Given enough time, particles randomly moving through the void could, purely by chance, come together in just the right way to form a fully conscious brain, complete with memories, thoughts, and experiences. This self-aware entity, a Boltzmann brain, would believe it had lived an entire life, that it had a past, that it was part of a meaningful universe, when in reality, it was just created seconds ago, destined to dissolve back into nothingness. And here's where the paradox destroys everything you think you know. If the universe is infinite, then Boltzmann brains should vastly outnumber real observers. Why? Because assembling an entire orderly universe takes far more improbable coincidences than assembling a single thinking brain floating in empty space, which means it is statistically more likely that you are a Boltzmann brain than a real human living in a stable universe. Yes, you might not be a person at all. You might be a brief, accidental fluctuation in the chaos of the cosmos, spontaneously blinking into existence with a set of fake memories, experiencing this moment right now, only to vanish an instant later, never having actually lived at all. And the worst part? You could never know. If all your memories were artificially constructed by a random fluctuation, how could you tell the difference between reality and illusion? If your experiences, your knowledge, even your belief in science and logic were nothing more than a temporary trick of entropy, then what does it mean to know anything at all? The Boltzmann brain paradox is a crisis of probability. It suggests that in an infinite, chaotic universe, intelligence and consciousness are not signs of order, but of randomness. It challenges our fundamental assumption that we exist in a coherent reality, instead forcing us to consider a far darker possibility, that this, right now, is nothing more than a cosmic hallucination, an accident of thermodynamic noise. So, if that's true, what should you do? Maybe nothing. Maybe in the next second, you will dissolve, and none of this will have ever mattered. Or maybe the very fact that you are questioning your existence means you are something more than just randomness. But how can you ever be sure? The simulation hypothesis paradox. If we create simulations, how do we know we're not in one? Right now, you feel real. You see, hear, and touch the world around you. Your thoughts seem authentic. Your memories consistent. You assume your experiences are unfolding in a genuine, physical universe. But stop for a moment. How do you actually know? This is the simulation hypothesis paradox, a mind-breaking question that suggests reality itself might be artificial, a digital illusion, a program running on an advanced system beyond our comprehension. The argument is simple but devastating. If humanity ever develops the ability to create ultra-realistic, conscious simulations, then there is no reason to believe we are in the original reality rather than one of the countless simulations that would follow. Think about it. Video games have evolved from simple pixels to photorealistic worlds. Artificial intelligence is learning, improving, mimicking human behavior. Now, imagine a future where technology advances to the point where we can simulate entire conscious beings indistinguishable from reality. At that point, one of three things must be true. 1. Civilizations never reach that level of technology before going extinct. 2. They reach it but never create simulations. 3. They reach it and create billions of simulations. Now, consider this. If advanced civilizations do create millions or even trillions of conscious simulations, then statistically speaking, the number of simulated beings would far outnumber the original biological ones, which means it is vastly more likely that we are living inside a simulation than in base reality. And here's where the paradox destroys your certainty about existence. If you are in a simulation, then everything you know, your senses, your body, your planet, even the universe itself, might be nothing more than data inside an inconceivably powerful machine. Your experiences are not reality, but code. But if we are in a simulation, could we ever know? What if the simulation is perfect, designed to keep its inhabitants from discovering the truth? What if the laws of physics we observe are simply rules programmed into the system, constraints written into the simulation's code? And what about them? Whoever is running the simulation, are they like us, future humans testing out digital realities? Are they something beyond our understanding, godlike beings shaping countless simulated worlds? Or are they simulated too? If they created us, who created them? If their world is also a simulation, how deep does it go? This paradox hints at a horrifying possibility, an infinite chain of simulated realities stacked on top of each other, each believing they are the original, each unaware they are just a program within another program. And here's the real nightmare. If we ever do create fully conscious simulations, we would prove that simulations are possible, meaning the odds that we are in one right now skyrocket. If you can create a reality that fools its inhabitants, then why assume you're in the only real one? But if we are in a simulation, what happens when it ends? Do we get erased? Do we wake up somewhere else? Are we experiments, entertainment, or something we cannot even comprehend? Or maybe the only reason you even feel the urge to ask these questions is because something in the simulation wants you to. So now, ask yourself one final question. Are you really reading this? Or is it just part of the program? The paradox of consciousness. How can self-awareness emerge from inanimate matter? Right now, you are aware, not just existing, not just functioning, but knowing that you exist. You have thoughts, you feel emotions. You can reflect on your own existence and ask, what am I? But stop for a second. Look at your hand. It's made of atoms, the same kind of atoms that form rocks, water, and air. The neurons firing in your brain are built from simple particles, obeying physical laws with no hint of thought or awareness. So here's the paradox. How does non-conscious matter suddenly become conscious? This is the paradox of consciousness, a problem so profound that it threatens to collapse our entire understanding of reality. It asks, how does self-awareness emerge from things that have no awareness? At first, you might think it's just complexity, that when enough neurons connect in the right way, consciousness just appears. But why should that be true? Why should assembling billions of unconscious atoms into a complex system suddenly create a first-person experience? A computer processes information, yet it does not feel anything. A rock exists, but it is not aware of itself. So why should you be any different? Some scientists believe that consciousness is just an illusion, a byproduct of the brain's computational processes. But that doesn't solve the problem. It just avoids it. Because even if it's an illusion, who is experiencing the illusion? And here's where things get even stranger. If consciousness is just a product of brain activity, then what happens if we slowly replace every neuron in your brain with an artificial one? If the function remains identical, would you still be there? Or would you gradually be replaced by a perfectly functioning machine that feels nothing? And if a machine can't be conscious, then why are you? Some theories suggest that consciousness is not something that emerges from matter, but something fundamental to reality itself, that it doesn't arise from physical processes. It is a property of the universe, like space, time, and energy. But if that's true, then what does it mean to be alive? What if everything, even a rock, even a single atom, has some primitive form of consciousness? What if what you experience as self-awareness is simply a highly developed version of something that exists everywhere, all the time? Or take it a step further. What if consciousness is not something your brain produces, but something your brain receives, like a radio picking up a signal? What if your mind is not inside you, but outside reality, with your body acting as nothing more than a biological antenna? The paradox of consciousness is terrifying because it exposes a fundamental gap in our understanding. We know how to describe atoms, forces, and interactions, but we have no idea how those things create an inner experience. And if science cannot explain what you are, then how much of reality do we actually understand? Perhaps the greatest paradox of all is this. You can study the universe, but the one thing you can never fully understand is yourself. The genetic bottleneck paradox. How did humanity survive when only a few thousand ancestors existed? Right now, there are 8 billion humans on Earth. We fill cities, nations, entire continents. But at one point in history, according to genetic evidence, our ancestors were reduced to a terrifyingly small number, perhaps only a few thousand. Think about that. Humanity almost didn't make it. This is the genetic bottleneck paradox, a mystery that asks, how did we survive near extinction when small populations usually die out? In biology, genetic diversity is critical for survival. The more diverse a population's genes, the better its chances of adapting to disease, environmental changes, and evolutionary pressures. But when a species goes through a bottleneck event, a sudden, drastic reduction in population, its genetic diversity shrinks. And when diversity shrinks, so does the ability to survive. If human ancestors were truly reduced to just a few thousand individuals, then the paradox is clear. Why didn't we go extinct? Most species that suffer such a severe loss never recover. They become vulnerable to genetic disorders, environmental threats, and simple bad luck. With such low numbers, a single disease could have wiped us out before civilization even began. So why didn't that happen? The genetic evidence suggests that humans faced multiple bottlenecks, times when our numbers dropped dangerously low. One of the most famous hypotheses suggests that around 70,000 years ago, a massive volcanic eruption, Mount Toba, triggered a global climate catastrophe. This event may have caused our population to plummet to as few as 1,000 breeding individuals. That's smaller than some endangered species today. But instead of vanishing, humans not only survived, we spread across the entire planet. How? One possibility is that human intelligence was our saving grace. Unlike other species, early humans had technology, cooperation, and adaptability. We may have survived by sticking together, sharing knowledge, and changing our behaviors in ways that other species could not. Another explanation is that our genetic diversity wasn't as lost as we think. Even though the population was small, our ancestors may have lived in multiple isolated groups, preserving variations of DNA that later mixed back together when populations reconnected. And then there's the truly unsettling possibility: what if other human species did not survive? We know that early humans weren't alone. Neanderthals, Denisovans, and other hominins once roamed the earth alongside us, but today, only one human species remains: us. Did our ancestors outcompete them? Absorb their DNA? Were we just luckier? The genetic bottleneck paradox raises deeper existential questions. How close did we come to never existing at all? If events had played out just slightly differently, would humans have been nothing more than a failed evolutionary experiment? And could this happen again? Could another catastrophe reduce us to the edge of extinction once more? The paradox forces us to recognize how fragile our existence truly is. We walk the earth as if we are inevitable, but our very survival may have been a statistical fluke, a near impossible escape from extinction that could have erased us from history before history even began. And yet, here we are, which means the real question isn't just how we survived, but what it means that we did. The missing link paradox. Where are the countless intermediary species between evolutionary stages? You've seen the classic image, a monkey slowly evolving into a modern human, step by step. Evolution, we are told, is gradual, one tiny change at a time, with countless transitional forms bridging the gaps between species. But if evolution happens in small, continuous steps, then here's the paradox. Where are all the missing links? If every species evolved gradually, then the fossil record should be overflowing with intermediates, creatures caught mid-transition between one form and another. Instead, we find long periods of stability, with species barely changing for millions of years, followed by sudden leaps where new species appear seemingly out of nowhere. This is the missing link paradox, a mystery that has puzzled scientists since Darwin first proposed his theory of natural selection. At first, the answer seems simple. Maybe we just haven't found enough fossils yet. The fossil record is incomplete. After all, fossilization is rare, and most life forms decay before they ever leave a trace. But even as we discover more fossils, the pattern remains. Homo habilis existed, then suddenly Homo erectus appeared. Dinosaurs ruled the earth for millions of years, then suddenly vanished, replaced by an explosion of mammals. The Cambrian explosion, one of the greatest evolutionary leaps in history, produced a staggering variety of complex animals in a relatively short geological time frame. Evolution is supposed to be gradual, so why does it often look sudden? Some scientists argue that evolution doesn't happen at a constant rate. It happens in bursts. This idea, called punctuated equilibrium, suggests that species remain stable for long periods, only evolving rapidly when their environment changes drastically. Instead of a slow, steady transformation, evolution might work like a series of sudden rewrites, where species evolve quickly in small, isolated populations and then spread. But this still doesn't fully solve the paradox. If evolution is always happening, why don't we see living transitional forms? Where are the half-fish, half-reptiles, or the creatures halfway between birds and mammals? Why do species seem to appear fully formed without endless intermediate versions filling the world around us? The unsettling possibility is this. Maybe evolution doesn't work the way we assume. What if species don't evolve in tiny, gradual steps, but instead in unpredictable leaps? What if certain mutations occur in large transformative jumps, creating what appear to be sudden new species instead of slow transitions? Or take it further, what if we are missing something entirely about how life evolves? Could external forces, catastrophic events, cosmic radiation, even mechanisms we don't yet understand, reshape evolution in ways we haven't discovered? Could life be driven by more than just random mutation and selection? The missing link paradox forces us to confront the mysteries still lurking within evolution. We think we understand how life developed, but when we look closely, gaps remain, gaps that suggest evolution might not be as smooth, predictable, or even fully understood as we assume. And if that's true, then the story of how we got here is still incomplete, which means the biggest missing link might not be in the fossils, but in our own understanding. The Toxin Paradox. Can you intend to drink a toxin that you won't actually drink? A billionaire approaches you with a strange proposition. On the table, there's a vial of toxin. It won't kill you, but it will make you extremely sick for a full day. Here's the deal. If by midnight tonight, you can genuinely intend to drink the toxin tomorrow, the billionaire will wire $1 million into your bank account. The money will be there instantly. No tricks, no strings attached. But here's the twist. You don't actually have to drink the toxin. You just have to intend to drink it. Once the money is in your account, you're free to change your mind and walk away. Now, the paradox sets in. At first, it seems easy. Just decide to drink the toxin, get the money, and then don't drink it. But can you really intend to do something when you already know you won't follow through? Intention is more than just saying you'll do something. True intention means that if the future arrives as expected, you will act on your decision. But once the money is in your account, there's no reason to drink the toxin anymore. So can you ever truly form a real intention to drink it? The paradox destroys your ability to plan rationally. If you know you won't drink the toxin, then you can't genuinely intend to drink it in the first place. But if you can't intend to drink it, then you won't get the $1 million. So what do? Some people suggest you could trick yourself, convince yourself that you will drink it, even though you actually won't. But can you truly deceive yourself if you're fully aware of what you're doing? Others argue that the only way to win is to have a different kind of mind, one capable of intending something without requiring future follow-through. But if that's the case, what does intention even mean? This paradox shatters our understanding of decision-making, free will, and rationality. It exposes a disturbing truth. Sometimes, there is no logical way to intend something you know won't happen. It raises deeper questions. Can we ever truly control our future actions? Is intention separate from action, or are they inseparably linked? And if we can't fully control our own minds, who or what is actually making our decisions? The Toxin Paradox isn't just about a hypothetical game. It's about the fragile, unpredictable nature of human intention itself. And it forces you to ask, how many of your own decisions are truly yours, and how many are just illusions? The paradox of free will. If physics determines every action, do we have free will? Right now, you feel like you are in control. You can decide to raise your hand, close your eyes, or walk away. You experience the sensation of choosing, as if your thoughts originate from your own free will. But stop. What if every decision you make was already determined before you even thought about it? This is the paradox of free will, one of the deepest existential dilemmas in philosophy and science. It asks, if the universe operates by strict physical laws, how can free will exist? Think about it. Physics tells us that everything in the universe follows cause and effect. Your brain is made of atoms. Those atoms obey the same physical laws as everything else. If you rewind the universe to its beginning, every event, including every thought, every decision, should unfold exactly the same way, like a movie playing on repeat. Which means every choice you make is just an inevitable outcome of prior physical events. Your decision to read this? Determined by electrical impulses in your brain, which were caused by prior brain states, which were influenced by your genetics, past experiences, and the environment, none of which you truly chose. So if every decision is just physics unfolding, then how can free will be real? And here's where the paradox gets even worse. Neuroscience has found evidence that your brain makes decisions before you are consciously aware of them. Experiments show that when you decide to move your hand, the neurological activity that causes that movement began before you even thought about it. In other words, your brain decided for you before you felt like you made a choice. So, are you actually making choices, or is your consciousness just a spectator, watching decisions unfold as if they were your own? Some scientists argue that free will is just an illusion, a mental trick to make us feel like we are in control, when in reality, we are just complex machines running on pre-programmed physics. But if that's true, then what happens to morality, responsibility, and identity? If criminals had no real choice in committing a crime, can they be blamed? If every decision was predetermined, can anyone be truly praised or punished? And if free will is an illusion, what does it even mean to be you? Some philosophers try to escape this paradox by suggesting that free will and determinism can coexist. This is called compatibilism, the idea that even if our choices are influenced by physics, we can still have free will if those choices reflect our inner desires and reasoning. But this still doesn't fully solve the paradox. Are your desires really yours, or are they shaped by forces outside your control? If you grew up in a different country, with different parents and experiences, wouldn't you have entirely different desires, ones you never actually chose? And if the conditions that shaped you were out of your control, then are you really in control at all? The paradox of free will forces you to confront a disturbing possibility. Everything you have ever thought, felt, and decided may have been inevitable from the very beginning of time. So the question isn't just, do you have free will? The real question is, if you don't, could you ever truly know? The heat-death paradox. If the universe ends in entropy, why does anything still happen? The universe is dying, not in a dramatic explosion, not in fire or chaos, but in silence, in stillness, in the slow, inevitable fading of all energy until nothing remains but cold emptiness. This is the fate predicted by the second law of thermodynamics, which states that entropy, the measure of disorder, must always increase. Over time, usable energy is lost, stars burn out, and all matter drifts into a final equilibrium of cold, dark uniformity. This is heat death, the ultimate inescapable end of everything. But here's the paradox. If entropy is always increasing, why hasn't the universe already stopped? Why does anything still happen at all? Entropy should be pushing everything toward disorder and maximum equilibrium. The laws of physics don't favor complexity, they favor randomness. And yet, here we are. Stars are still burning, galaxies are still forming. Life is still thinking, evolving, creating. If everything is moving toward heat death, why hasn't it already arrived? This paradox hints at something deeply mysterious about the nature of time, existence, and causality itself. One explanation is that we're simply not there yet. The universe is vast, and though entropy is increasing, it takes trillions of years to reach total equilibrium. The processes we see, star formation, planetary motion, even thought, are just temporary ripples in a sea of inevitable decay. But that answer feels unsatisfying. It doesn't explain why low-entropy systems, like life, exist in the first place. Here's the real problem. For the universe to have high entropy in the future, it must have had low entropy in the past. But why was the early universe so orderly? Why did the cosmos begin in a state of extreme low entropy when all probability suggests it should have started as chaos? This is called the past hypothesis, and no one knows why it's true. If entropy must always increase, then it seems far more likely that we should already be living in a dead universe, a cosmic graveyard where time has stopped, where there is no energy left to power movement, light, or thought. But we're not. We are here, in a universe that still burns, still moves, still defies total disorder. Some physicists speculate that the answer lies in multiverses, where our cosmos is just one of many, each with different entropy conditions. Others suggest that entropy itself might be cyclical, with universes collapsing and rebirthing in an eternal loop. And then there's the truly mind-shattering possibility: what if time only exists because entropy increases? Some researchers propose that time emerges from entropy, that without entropy increasing, there would be no before or after, only a frozen, timeless void. If true, then we are not moving through time at all. We are simply experiencing the expansion of entropy, mistaking it for the passage of time itself. The heat-death paradox isn't just about the future of the universe, it's about why anything happens at all. It forces us to confront the eerie truth that everything we see, every star, every thought, every moment, exists on borrowed time, a temporary dance of order in a universe that is destined for stillness. And maybe the final paradox is this: if nothing can stop entropy from increasing, then the most fundamental question isn't how will the universe end? It's why did it ever begin? The Olbers Paradox. Why is the night sky dark? If there are infinite stars, step outside on a clear night. Look up. The sky is dark, speckled with the faint glow of distant stars. But stop. That doesn't make sense. If the universe is infinite, and if stars are spread throughout it, then every single point in the sky should eventually hit the surface of a star. The night sky should be blazing with light, as bright as the surface of the sun, because no matter where you look, your line of sight should eventually land on a star. So why isn't it? This is Olbers' paradox, a puzzle that has haunted astronomers for centuries. If the universe is filled with endless stars, then why does darkness exist at all? At first, the answer might seem simple. Maybe stars are just too far away. But distance alone isn't enough to explain the darkness. Even if a star is faint, an infinite number of them should still add up to overwhelming brightness. Another possible answer: maybe dust blocks the light. But that doesn't work either. Over time, dust would absorb light and heat up, eventually glowing just as brightly as the stars themselves. So why is space still dark? The answer to Olbers' paradox reveals something fundamental about the nature of the universe. One key factor is that the universe is not infinitely old. Light takes time to travel. If the universe had existed forever, then light from every star, no matter how distant, would have had infinite time to reach us. The sky would be a sea of unbroken brilliance. But our universe has a beginning. The Big Bang happened 13.8 billion years ago, which means we can only see light from stars within a 13.8 billion light-year radius. Beyond that, their light hasn't had enough time to reach us yet. And then there's another critical piece. The universe is expanding. As space stretches, the light from distant galaxies is redshifted, stretched into longer wavelengths, moving from visible light into infrared, then into microwaves, until it fades beyond what our eyes can see. This means that even though distant stars and galaxies exist, their light has been stretched into invisibility, leaving the sky dark. So the paradox isn't just about stars, it's about the structure of reality itself. The night sky is dark not because the universe is empty, but because it is young and constantly changing. But here's the real mind-bender. If the universe were truly infinite and unchanging, there would be no such thing as night. The darkness we see is proof that the universe had a beginning, that it is expanding, and that time itself moves forward. So the next time you look at the night sky, don't see emptiness. See evidence of cosmic history, of the birth of time, of a universe that is still unfolding. Because the real paradox isn't that the night sky is dark, it's that the darkness is full of light, just beyond what we can see. The fine-tuning paradox. Why do physical constants seem precisely set for life? Take a step back from everything you know, from the Earth, the Sun, the galaxy, from the atoms that make up your body, from the laws of physics that govern reality itself. Now ask yourself, why does the universe allow life at all? This is the fine-tuning paradox, one of the most unsettling mysteries in cosmology. It asks, why do the fundamental constants of physics seem perfectly calibrated to make life possible? Consider the numbers that shape reality. The strength of gravity. If it were just slightly weaker, stars wouldn't form. If it were slightly stronger, stars would burn too quickly for life to emerge. The electromagnetic force, if it were just a little different, atoms wouldn't hold together, and chemistry as we know it would be impossible. The cosmological constant, the force that determines the expansion of the universe, is so precisely balanced that a change of 1 part in 10 to the power of 120 would either collapse the universe in an instant or tear it apart before galaxies could form. The numbers don't just work together, they work together so perfectly that even the tiniest deviation in any one of them would render life, planets, and even stable matter itself impossible. So why? Why do we live in a universe where the laws of physics are just right for complex life to emerge? There are only a few possible answers, and each one is more unsettling than the last. 1. It's just a coincidence. Maybe we just got lucky. Maybe the universe is the way it is by pure chance, and if the constants had been different, we wouldn't be here to question it. But this explanation feels unsatisfying. The odds against these precise conditions are so astronomically high that calling it luck seems indistinguishable from calling it a miracle. 2. There's a deeper physical law we haven't discovered. Maybe these constants aren't random at all. Maybe they have to be this way, based on some yet undiscovered principle of physics. But if that's true, then the question shifts. Why does that deeper law favor life? If the laws of physics are determined by something even more fundamental, that still doesn't explain why those deeper rules allow a universe where stars burn, molecules form, and creatures can ask questions like this. 3. The multiverse. There are infinite universes, and we just live in one that works. This is one of the most popular explanations, the idea that ours is just one of countless universes, each with different physical laws. Most of those universes would be dead, lifeless, or completely unrecognizable. But in an infinite set of possibilities, at least a few will have the right conditions for life, and we just happen to be in one of them. This explanation resolves the paradox statistically, but it introduces another mystery. If the multiverse exists, why does this universe feel so real? Why does it feel like it was made for us? 4. The simulation hypothesis. The universe is fine-tuned because it was designed. The fine-tuning paradox has led some to an even stranger possibility. What if the universe is finely tuned for life because someone or something tuned it that way? Some scientists and philosophers speculate that our reality could be a simulation, carefully calibrated with just the right physical constants to sustain complex structures, planets, and intelligence. If that's true, then our universe isn't a random accident. It's a designed system, created for a purpose we may never understand. So what's the answer? The fine-tuning paradox forces us to confront one of the greatest mysteries of existence. Is life a cosmic accident? Is the universe part of a vast multiverse where countless realities exist? Or is there something deeper, something intentional, about the way reality is structured? No one knows. But what we do know is this: we exist in a universe that allows life, a universe that, against all probability, works. And whether that is an accident, a necessity, or something beyond our understanding, the fact that we are here to even ask the question might be the biggest paradox of all. The quantum suicide paradox. Does consciousness always find itself in a reality where it survives? You sit in a chair, staring at a deadly quantum machine. It is wired to a single subatomic particle, which will be measured in one of two states. If the particle is in state A, nothing happens. If the particle is in state B, the machine instantly kills you. The catch? According to quantum mechanics, before the particle is measured, it exists in a superposition, both states at once. When measured, the universe splits into two. In one universe, you survive because the particle was in state A. In the other, you die because it was in state B. Now, here's where the paradox destroys everything you think you know about death and survival. Let's say you repeat this experiment over and over again. From the perspective of an outside observer, your fate follows probability. Eventually, you will hit state B, the machine will fire, and you will die. End of story. But from your perspective, from the inside, something bizarre happens. Since consciousness can only exist in realities where you are alive, you will always experience the outcome where you survive. In every universe where you die, your consciousness ceases to exist. You can never observe your own death, because in every world where you would have died, you are no longer there to witness it. So if this logic holds, no matter how many times you run the experiment, your experience of reality will always be one where you somehow survive, even if it defies normal probability. And here's the paradox. Does this mean you are immortal? The many worlds interpretation. Are there infinite versions of you? This paradox emerges from the many worlds interpretation of quantum mechanics, which suggests that every time a quantum event occurs, reality branches into multiple parallel worlds. Most versions of you do die, but at least one version always survives. So no matter how unlikely your survival, there is always a reality in which you live. This leads to unsettling questions. If you attempt something statistically impossible, say surviving a gunshot to the head, does your consciousness always end up in the one universe where you somehow live? Are you constantly shifting into less probable versions of reality, simply because your consciousness can never experience its own non-existence? And if this paradox is true, does that mean you will always exist in some form, forever, in some version of reality? The ultimate immortality. Is death an illusion? The quantum suicide paradox suggests that from your own perspective, you will never die. Because in every universe where you could have died, you are no longer there to witness it. Of course, to everyone else, you will eventually disappear. They will see your death in their reality. But your consciousness? It will keep jumping into timelines where you somehow keep going. But what happens at the end of the universe? If the universe itself decays and all possible realities eventually lead to destruction, then where does consciousness go? Or will it, through sheer quantum probability, always find somewhere to exist? The paradox forces you to consider a terrifying possibility. If the many worlds interpretation is true, then your consciousness is unkillable. You will always find yourself in some version of reality where you live, no matter how improbable. So now, ask yourself, are you here because you should be alive? Or are you here because, across infinite realities, this is just the one where you survived? The Doomsday Argument. If most humans exist, near the end of civilization, is the end near? Right now, you are alive. You are one of the billions of humans who have ever existed. But what if that very fact, your place in the timeline of humanity, is a warning that civilization is about to end? This is the Doomsday Argument, a chilling paradox that suggests we can use simple probability to estimate how close we are to the extinction of humanity. Here's how it works. Imagine a lottery where you are assigned a random number. You receive $85,000. Then you learn that there are only 100,000 tickets in total. That number should scare you, because it suggests the lottery is almost over. You just happen to be near the end. Now, apply this thinking to humans. You are a randomly chosen human out of all that will ever exist. Estimates suggest that about 117 billion humans have lived so far. If civilization lasts for millions more years, then trillions of future people should exist. But if that's true, why do you find yourself so close to the beginning rather than deep in the future, surrounded by trillions of others? Statistically speaking, the most likely explanation is this. You exist now because the end is near. If humanity were going to last for millions of years, the odds of you being born this early in history are astronomically small. But if we are much closer to the end, suddenly your position in time makes perfect sense. You are one of the last humans, just as someone with lottery ticket 85,000 should suspect the game is almost over. The paradox deepens. Can we really predict doom with probability? At first, this argument sounds absurd. How could pure statistics predict the fate of civilization? But it follows a simple mathematical principle. If the human population were to grow for millions of years, most humans would exist far in the future. But since you exist now, you are far more likely to be near the middle or end of civilization's timeline, not the beginning. Therefore, it is more probable that we are closer to the end than the beginning. How close are we? Depending on the assumptions you use, this argument suggests that humanity may only have a few thousand more years before civilization collapses. If our total human population will be around 200 billion, then we are already well past the halfway point. If it will be trillions, then we are still early. But if civilization is short-lived, then we are exactly where we should expect to be, right before the final generations. What could cause the end? The Doomsday Argument doesn't tell us how humanity ends, only that we should expect it to happen sooner rather than later. But possible threats are everywhere. Nuclear war, climate collapse, artificial intelligence, pandemics, global economic failure, cosmic disasters, asteroids, gamma-ray bursts, etc. Any of these could bring civilization to an end far sooner than we imagine, and if the Doomsday Argument holds, one of them will soon. Escaping the paradox, can we beat the odds? Some argue that the Doomsday Argument only applies if humans remain on Earth. If we colonize space, the total number of future humans could expand into the trillions, pushing us back to the early part of the timeline. Others claim the argument relies on faulty probability. Perhaps human history isn't like a lottery, and our position in time doesn't mean anything. But the paradox remains unsettling. If humanity is doomed to last only a short time, then we are exactly where we should expect to be, right before the end. So now ask yourself, are you lucky to be living in the middle of human history, or are you part of one of the final generations, on the edge of civilization's last days?